that a
Right.
probability measures.
Well, we don't even have to talk about probability when we talk about random variable. What is a random variable is a function, right? Do you know what it's defined on? So this is a bit of a recap.
The sample space.
Right. It's defined on the outcomes of a sample space, right? And for each of those outcomes, we have a particular real value, or we have a particular number associated with that outcome. Okay, hold on. Could it be pardon me, could it be your audio from your end? It's kind of unfortunate you can't hear me. So Olivia says, do you have headphones plugged in? I'm not sure if he does. So I was suggesting earlier, if it's possible, there's a mute button, right? On Zoom, there's a mute button, and right next to it, there's like a little caret, like a little arrow symbol. And then if you click on that, there's an audio settings um, feature that comes up. So maybe that can help with turning on the audio from your end. Sorry, guys, give me 1 second. Hey, guys, sorry about that. There was a bit of a technical difficulties that one of the people here was experiencing. So apologize for the wait. Okay, so let's continue with what a random variable was, right? So what is a random variable again? We said that it was a yes.
You're not sharing your screen.
I'm not sharing my screen. Thank you. I am not sharing my screen. I'm writing something down and you guys don't see it. There we go. Okay. So a random variable is a function, right? So we've talked about functions for a long time. For those of you who studied mathematics, right? Monday, that's right. It's always those Mondays, right? We don't want it to start on a Sunday. We're thinking about, oh man, it's gonna be Monday tomorrow, and then Monday hits you, and you're like, what? But anyways, so a random variable is a function that is defined on the outcomes of a sample space in a probability experiment. So the outcome of the sample space, that becomes your input, right? Remember when we talk about functions, we have an input and an output. We have an independent variable and a dependent variable. So our independent variable, or our inputs to this function called a random variable, are the outcomes of a sample space, the events of a sample space, right? In a probability experiment. And the output of this function is a number. That's all it is. It's simply a number, a real number. So it is a function that is defined on the outcomes of sample space in a probability experiment and has a number. Now I'm going to just use the word real, a real number associated with each outcome. And this real number is my outputs. Okay, so that's how these functions are. They're functions that are defined particularly on the sample space of a probability experiment. So the moment you have this kind of function, you have what's called a random variable. Okay. Okay. Now let me give you oh, great. Great. I'm glad you can hear me. Awesome. Okay, so just like a little quick example. Let's suppose again with these examples of urns, right? An urn contains 5 red, 3 orange, and 2 blue marbles. Okay, so we have this kind of typical probability experiment where we have an urn and we have different colored marbles. And then we say 2 marbles are randomly selected. Okay, and then we can define. So that's the thing that maybe is a little bit new to some of you, right? We can actually define a random variable in more than one way. So I'm going to define it like the following. I'm going to say let x, and normally remember we consider random variables with capitalized letters, and particularly we're going to use the capital X to denote a random variable. So let x represent the number of orange marbles selected, right? Now, who can tell me what are the values associated with this random variable? So I just defined my random variable. So this is the definition of a particular random variable, definition of a particular random variable x. So what are the values? The values of x are, can anyone tell me? So Mir says 0, 1, 2, 3. And Fang, Daisy says 0, 1, and 2. So Mir, where do you get the 3 from? And then Hijab also says 0, 1, 2, 3.
Right.
So we have 2 people that have said 0, 1, 2, 3, and 1 person has said 0, 1, and 2. Yes, Mir.
No, Fang is right.
Daisy, you're right. Oh, how come? How come she's right?
Because you're only choosing 2.
Right, right. So if you look at the scenario a bit more, it says 2 are randomly selected, right? So our probability experiment deals with selecting 2 marbles out of the 5 plus 3 plus 2, which is out of the 10 marbles overall. We're only selecting 2. That's the way our experiment is defined. We can change that number 2 to 3 to 4 to 5 to 10, right? But we're saying this is 2 marbles that we're selecting. So out of these 2 marbles, we're defining a function that gives us the number of orange marbles that are selected out of the 2. So there's only 3 possibilities, right? So either x can equal 0, which means I have 0 orange marbles selected out of the 2. Okay, so 0 orange marbles. Are selected out of the 2 selected, right? Or we can have our random variable equaling 1, which denotes 1 orange marble, right? Selected out of the 2. And then lastly, we can have two orange marbles. Selected out of the 2 chosen, right? So again, this is just a brief example of how these kind of random variables appear, how we're able to now have a more systematic way of expressing our probability experiment. Instead of saying this statement every time, instead of saying this, oh, this is what we're doing, we just really just encapsulating all of this words into a single variable, into a single letter. So this letter is saying this every time. Every time we write this letter down, X, and of course it's a capital letter X. So sometimes they like to include this just to make sure we're not saying that little x is equal to 1, 0, 1, or 2. We're saying that big X is equal to 0, 1, or 2. Now, of course, we don't end here, right? We don't just talk about what the values of X can be. We actually we go a little bit further. We care about what the probabilities associated with that value for the random variable is. So, so these are the possible values of X. And just to understand what's going on, what's the probability that my random variable X attains the value of 0? So now we're going to a new dimension here, probability. And we're going to talk about, we talked about this last time, probability mass function, right? This is where we're going to be heading into. So can anyone tell me what's the probability that my random variable attains the value 0? Which means how do we translate these letters and symbols? We're saying what's the probability that when I select 2 marbles, I get no 0 orange marbles? So how do we compute this probability? Or maybe before we do that, how do we interpret this event, having 0 marbles that are orange? What's another alternative way of expressing or describing this event when X equals 0? How else can I rephrase this? The complement. So yeah, so exactly what do you mean by the complement? The complement of what? Of what exactly?
X.
Hmm?
Of X.
But can you be more explicit? So what does X represent again? It represents the number of orange marbles that come up out of the 2 marbles that are selected, correct? So then what I'm asking is, if I have 0 orange marbles out of the 2 selected, what's another way to say that? Yeah, exactly. Thank you, Daisy. Right. You get marbles that are not orange. So they could either be all red, they could be all blue, or they can have a mixture of one being red and one being blue. So that's the idea. So this means I'm not selecting. So I'm selecting 2 marbles that are not orange. That are not orange. So it could be red or blue. So how do we find that probability, guys? You guys should be experts at this. You guys took an exam on finding probabilities, right? So this is a typical probability question, basic probability question. So how many are not orange? So Ethan says 1 minus the complement, right? That's what you did. You did 5C2 plus 5C1 times C2. Okay, so you did all of that. But how many are not orange again? How many oranges do we have? We have 3 oranges, don't we? So 7 are not orange. Thank you. 7 are not orange. So if 7 are not orange, isn't this what we want? So can't we, so isn't this exactly what I'm trying to figure out? If none of them are orange, then how many do I want to choose out of these orange, not orange group? I want 7 choose 2, right? So I can write this as the binomial coefficient 7 choose 2, right? This would give me all the ways that I would select not an orange marble. And then I'm going to divide that by out of the total, right? What's the total number of ways? 10 choose 2, right? And then I'm able to compute this. 7 choose 2. What's 7 choose 2? Isn't it 21? And then what's 10 choose 2? Isn't this 45? So then, and you can reduce this, can't you? Divided by 3, right? This becomes a 7. Pardon me, this becomes a 7. And this becomes a 15. So what did I just find? I found the probability that's associated with what? My random variable equaling 0. And again, what's my random variable associated or defined as? It's defined as the number of orange marbles that have come up out of the 2 marbles selected from this urn. So instead of writing all those things I just said down, I write simply probability of x, curly braces, x equals 0. And of course, even this becomes too much to write sometimes, right? So to denote this, even to abbreviate this notation here, we actually use this. They're the same thing. So just note that we're going to be using this kind of notation. So the probability that of little x is equal to the probability that the random variable x, uppercase x, equals a small little value, little x, okay? So this little x is the output of the random variable. Yeah, that is little p. I know it's not a, so these are lowercase, okay? These are lowercase letters, lowercase. This is uppercase. This is lowercase. Again, we're just getting used to the semantics, used to the notation. Okay, so eventually we're not going to be writing this out all the time anymore. We're just going to be writing little p of x. But what you should always remember is that this is denoting the probability that my random variable is equal to this number x. That's all I'm saying. So this here means what we just mentioned, that the probability that my random variable equals 0 is 7 out of 15. Okay, and then we can continue, right? We can continue finding what the probability of 1 is, which would be what's the probability of me getting 1 orange marble? And then what's the probability that 2 is? What's the probability that I get 2 random variable, 2 orange marbles, right, out of the 15? So when I find all of these things here, I find what's called the probability mass function also known as PMF. So this is a abbreviation, right? PMF, the probability mass function. So the random variables that we're dealing with, that we're going to be dealing with, has what's called the probability mass function associated with it. And then we'll start to see that there are certain random variables that have a specific structure behind their probability mass functions. We talked a little bit about the Bernoulli random variable last time and the binomial random variable. And we left off with one of those examples for the binomial random variable. And I plan to go back to that example because I don't think we finished it last time. So what would be the probability that you get one orange marble? So can we compute that? So remember what this means. This means that the random variable x is 1. What does that mean? That means that I have one orange marble. So how would you compute that? If I have one orange marble, that means that the other marble could be red or it could be blue. So what's the probability that I get an orange marble? One orange marble. I have 3 to choose from, right? But then how many do I have for the blue, right? I have 5 red and I have 2 blue. So either, remember this is an or question. This is either I get one red, one orange, or I get one red, I get one blue. Do you see that? Do you guys see that? So this random variable here, this value is associated with the outcomes that I get one red, one orange, or I get one red, one blue. So if I get one red and one orange, how many reds do I have again? I always forget. I have 5 red, right? So this here should be 5. I have 5 choose one ways to selecting red, and I have how many red, orange? I have 3 choose one to get an orange, right? So this is red, and this is orange. But then I have to add the other of probability, or the other way of counting one red. Sorry, this should be orange, not red, because we're talking about orange, right? So either we have one blue, and what's blue? Blue is where is this? 2 blue, right? So there's 2 blue. So I get 2 choose 1 blue times 3 choose 1 orange, right? So this is blue and this is orange. And then I divide that by the total number of ways, right? 10 choose 2. So 5, again, this is 5 times 3 plus 2 times 3, which is over 45. We already computed that last time. I'm confused. I thought X was the number of orange marbles. It is. I corrected it. Okay. Yeah, X is the number of orange marbles that come up out of the 2 selected. So here we have 15, right? 15 plus 6 over 45, which is 21 over 45, which is 7 out of 15. Correct, guys? Are we here so far? Does this make sense so far? Do you see how we're building up from what we've learned about just computing probabilities? Now we're a bit more systematic with it. Now this starts to become part of the description of a random variable. Yes, Mir.
Why do I have to look at the red and blue separately? Why can't I just do 7 choose 1?
What do you mean 7 choose 1?
I do 3 choose 1 to choose 1 orange, and then 7 choose 1 for any other one.
Yeah, you could have viewed it as that as well. You could have. It's the same, right? So what you're saying is I'm choosing one orange, which is 3 choose 1 ways, and then I'm choosing a one that's not orange. That's 7 choose 1 ways. It's the same thing. So that's right. Yeah, it's the same thing. I just did it this way so I can like also explain what this means in terms of events,
Okay,
mutually exclusive events, right? You have one red and one orange, or you have one orange and one blue. But if you viewed it that way, that's perfectly fine. Here. Okay.
thank you.
Yeah. And so lastly, what is P of 2? P of 2 is when your random variable has a value of 2, which implies that you have selected 2 random variables, right? 2 orange marbles, correct? So what is that going to be? So if I get 2 orange marbles, what is that going to be? 3 choose 2 out of what? 45, 45, right? But what is 3 choose 2? Isn't it 3 out of 45? So there's 3 orange marbles that I can select 2 from. And there's 3 different ways for doing that. And then the 45 on the bottom again is the total number of ways of selecting 2 marbles out of the 10. And then this reduces to what? Isn't this 1 out of 15? So this is 1 out of 15. So what we just calculated, guys, again, is the probability mass function of this particular random variable. So this is the probability mass function. This explains the probabilities associated with my random variable attaining these values 0, 1, and 2. And what do you notice? What do you notice if I were to add these probabilities? What do I get? I get 7 out of 15 plus 7 out of 15 plus 1 out of 15, which is 15 out of 15, which equals 1. This makes sense, doesn't it? So our random variable, the probabilities associated with this random variable adds up to 1. Because we defined a particular experiment. And so we've exhausted all possibilities of our random variable attaining these values. So if I accumulate all of these probabilities, it should give me the probability of being of all those probabilities associated with the random variable being 1. Again, the random variables are defined on the outcomes of the sample space of my particular probability experiment. So this exhausts all of our possible ways of selecting these 2 marbles. So henceforth, we have a probability that adds up to 1. The probabilities add up to 1. And so this is a fact. So if I take all the probabilities associated with the values of the random variable, they should add up to 1. Where P of xi, right, is equal to the probability that my random variable attains the x sub I value. And this attains all the probabilities associated with these values. So for every single value of x, the probability associated with that value for a random variable x. If we add all those probabilities up, they should always add up to 1. Always. Okay, so we talked about probability mass function. We've talked about the random variable. We talked about how the probability mass functions, the probabilities for the random variable all add up to 1 when you add them up. That's another way to check if you're doing everything correct. Okay, and so the examples that we've discussed last time, so the examples of discrete random variables. Okay. So this word discrete, remember this word has a certain this definition. A discrete random variable, or just the word discrete. Discrete means that it is a number that is finite, or what people call countably infinite. In other words, discrete just means something you can count, something you can associate with the natural numbers or the counting numbers, 1, 2, 3, 4. So if you have something that you can count, literally associate a number with it, whether it be an infinite number or it be a finite number that stops, if you can just associate a number to it, it becomes discrete. Things that are not discrete, or we're going to be talking about continuous, that's when it's something that you can't just choose a counting number to associate it with that thing. It's a little bit sometimes hard to distinguish, right? Or to identify a continuous, what's continuous, but something that's continuous, for example, is the interval, people use this a lot, 0 to 1. So choose anything between this interval 0 and 1, it's actually uncountably infinite. The number of numbers within this interval is uncountably infinite. There is no way to associate a counting number with everything that's within that interval. So we call that uncountably infinite. So we talked about 2 of them, right? One of them was the Bernoulli. The Bernoulli random variable. So this is like the beginning of discrete random variable. This is like where we start. So does anybody remember what the Bernoulli random variable, what that represented?
A binary outcome.
Right, it's a random variable, right? So we call this X. And it has 2 possibilities, right? So it has 2 values. Either it's a 1 or a 0, right? And this is if we say X has a success, or if X has a failure. So we like using these words, success and failure, to denote a binary, like you said, like you mentioned, Mir, a binary outcome. And associated with, so on top of that, it is just a single trial. It is a single trial or experiment or event. We just apply it one time, a single trial with only 2 possible outcomes. These are the values of this random variable, values of X. You can have a success or a failure, right? The 2 possible outcomes are the success or the failure, whatever that means. within the context of your problem, whatever that means. So if you flip a coin, for example, that's a very standard Bernoulli random variable. You flip a coin once, you have two outcomes, either, and this is up to you. You decide whether the heads is the success, which means that the tails is the failure, or the tails would be the success and the heads is the failure. That's up to you how you define it. And then associated with that is the what? The PMF, isn't there? What's going to be the probability mass function of my random variable, my Bernoulli random variable? Well, I can either have a success or I can have a failure. And normally we just call our probability of having success, we just call it P. Whatever P is, whatever that value is. Of course, P is a number between 0 and 1, right? That's the probability. So the probability that I have a success is some probability, and we call it P. So this is some probability. Some value between 0 and 1. So if my probability of my random variable being a 1 is P, then the probability of the complement, which is the probability of getting a failure, probability that my random variable equals 0, would be what? 1 minus P. Right? So far, that's the way we define our PMF. And again, very simple, right? This is a very basic, fundamental random variable. Because then from here, where do we go? We go to the binomial random variable. So we go from the Bernoulli to the binomial. And so what is the binomial random variable? How do we go from Bernoulli random variable, which is just one, it's just one trial, to a Bernoulli? Right, you're really just repeating the trial n or more than one time, right? So the Bernoulli random variable, what is the Bernoulli random variable associated with? It is when it is the number of successes when n independent trials, pardon me. And you could think of each trial as a Bernoulli, right? As a Bernoulli random variable. Are performed where the probability of a success is P, and the probability of a failure is 1 minus P. So here, we care about the success, whatever that's defined as. So let me see if I have. I think I have a good example for that. Okay, I'll give you an example. Suppose a coin has a probability of 0.7 coming up with suppose it has a probability of 0.7 to land on tails. I mean heads, to land on heads. The coin is flipped 3 times. Let X denote the number of heads that appear find the PMF of X. So do you guys see that I'm flipping a coin, right? If I flip it 1 time, and I have a probability that either it lands on heads or it lands on tails. So the flipping a coin 1 time can be associated as a Bernoulli random variable, right? This is where I have either probability of landing on heads or probability of that it lands on tails. But instead of doing it 1 time, I do it 3 different times. And then I'm saying let X be the number of times that heads appears when I flip it, when I flip the coin 3 times. So first of all, what are the values of X? What are the values of X in this case? So X can equal what? Everyone following me? What are the values? How many different number of heads can I have in this experiment here? Right, this is the one where it could be 0, 1, 2, or 3, right? You can either have 0 heads. You can say I have 1 head among the 3 times that I flip it. You can have 2 heads, or you can have a total of all 3. Right? And so then, what's the probability that I have no heads? Right? This is the probability of no heads, So how would I compute that? If I have no heads, then I have all tails for every single coin flip. So what's the probability of me getting all tails? Well, the probability of me getting a success, what's the probability of me getting success? This is my success, right? This is equal to P. P is equal to 0.7. Right now, people started saying 0. Yeah, exactly. So if this is a probability of success, then I know immediately, what do I know? The probability of failure. You guys see that? Probability of failure is immediately 1 minus 0.7, which is 0.3. So that means that this would be no heads. I would have 0.3 times 0.3 times 0.3, which is 0.3 cubed. That's when I have something like this. Tails, then tails, then tails. What's the probability of me getting tails? 0.3. What's the probability of me getting tails again? 0.3. And what's the probability of me getting tails again? 0.3. Why do I multiply? Because each of these events are independent. You see how that comes up again? The idea of independence. And that's what we talked about. They're independent of each other. Each trial that we make, the flipping a coin the first time is not affecting me flipping it the second time. So those are independent trials. So that's one of them, right? 0.3. And I want to write this down, 0.3 cubed. So the probability is 0.027, right? Okay. What's the probability that one of them, only one of the 3 coins that I flip, only one of them is a heads? How would I compute that? 1H, right? So Alexandra says 0.7, right? You said 0.7, and then you have 0.3 twice, right? So I'm gonna write that as 0.3 squared. Is that complete though? Because that probability that you gave me, Alexandra, is when you have the first one being heads and then the next 2 being tails. That's one way, right? But then can I also have it this way? Can I have this as tails, then heads, then tails? And then can't I have this as tails, tails, then heads? Yeah. So very good, Mir. There's a way to write this, right? Instead of me writing each individual probability and then adding them up, I can also think, oh, well, I already know that each of these outcomes are going to have the same probability. This particular event, right, of having one head, each of these outcomes has this equivalent probability, which is 0.7 times 0.3 squared. But my question is, how many of these outcomes are there? Well, it's the same thing as asking, of these 3 flips, I want one of them to be the flip where it comes up to be a head. And what is that number? It's 3 choose 1, which happens to be 3. So you can compute that, right? You can put that in your calculator. And I want to show you guys how to do that in your calculator. So eventually, this is a simple example, right? There's only 3 flips, but then there's other examples where there's a lot more, a larger number for n. So I want to show you how you can actually do that in your calculator, TI-83. So let me share my screen real quick. So if you have the TI-84 calculator, you can go to second vars. And then you get to this place called distribution, DISTR, distribution. And you have all these different things that we'll talk about some of these, not all of them. Talk about most of them. But there's this thing called the binomial. We're dealing with binomial PDF. Okay. So if you click on that, they ask you for a certain number of things. So the first one is the number of trials. So in this case, we have 3 trials. So this is our n. Okay, this is like our n parameter. The number of trials is one of the first parameters of the binomial distribution. P represents the probability of getting success. Our success is what? 0.7. So I'm gonna put 0.7. And x, the x value is the number of successes. In this case, we want one of them being the heads, right? One head. So when we paste that, this number that we get is exactly the number that we would get if we multiply 3 choose 1 times 0.7 times 0.3 squared. Now, I just want to show you guys again what we did in the previous computation. In the previous one, we wanted 3 trials, 0.7, and we wanted 0 heads. So let's see what this, just to be consistent, right? And we get exactly what we expected. Do you see that? So that's another way to compute the binomial probability, the probabilities for a binomial random variable. Does that make sense? Any questions about that? So this helps out with the computation itself, but you also have to understand how this computation actually works. Okay. So this number that we get should be what? 0.189, right? Do you guys see that? Okay, we're almost there. We're almost there. So then the next value is what? The probability that x is equal to 2. And then lastly, we have the probability that we have all heads. So what's the probability I get 2 heads? Does everyone see what's the way now? How do we compute this? Right, I could get two heads first. I can get a heads, then the last two are heads. And the other missing blanks are the tails. So what's the probability of one of these outcomes? Now I have two heads. So what happens with the probability of getting one head, right? So you get that 0.7 squared, right? I have 0.7 times 0.7, then I get 1.3. And then I want to figure out how many outcomes I have, how many possible outcomes are associated with this random variable equaling 2. It's the same thing as saying, hey, out of the 3 flips, I want 2 of them to be heads. So that's 3 choose 2 ways. And 3 choose 2 ways is 3. So again, I can put this in my calculator and I can actually compute it utilizing the procedure that I just showed you. And so I'll do that. So I want 2 heads and I get 0.41. So I get 0.441. So the probability of me getting 2 heads is 0.441. And then lastly, the probability of me getting all tails, pardon me, not all tails, all heads. Do you see? Now this is like saying, I want 3 of them to be heads. 3 of the 3 to be heads. That's 3 choose 3 ways, which is just 1. You see that? And in this probability, in this event, or this outcome, the probability of getting a heads is 0.7. And I'm doing that for each time I'm flipping a heads, which is 3 probability, 3 0.7s that I'm multiplying together. And then I can compute that. And I get 0.343. And again, the idea, so I've computed my probability mass function. The probability mass function is the probabilities of me selecting 0 heads out of the 3, 1 head out of the 3 is 0.189, 2 heads out of the 3 is 0.441, and 3 heads out of the 3 is 0.343. So I've defined my probability mass function. And if you add these up, they should add up to 1. If they do, then everything is clear. Everything should be good. So any questions about this particular example of a binomial random variable? Does this make sense? Yes. Yes. It's cool. That's right, Alexandra. It doesn't add to 1? Really? It should add up to 1. Hold on. Let me do this myself. 0.027 plus 0.189 plus 0.441 plus 0.343. It should add up to 1. Yeah, if you add these up, they add up to 1. So if I add from 0 all the way to 3 of P of I, right? Which is the same thing as saying the probability that my random variable equals I when I goes from 0 to 3, it should equal 1. And it does if you add them up. I just did it myself on the calculator, so good, right? Again, this is a specific example, but then I want to generalize this to any binomial random variable. So let's look at the general binomial random variable. So what are the parameters you can say? What are the things that make up a random variable, we want the number of trials, number of independent trials. And we usually just denote that with n. N represents the number of trials. And then what is the probability of success? Probability of a success. We usually denote that with a probability being P. P is somewhere between, P is somewhere between 0 and 1. So the probability of my success, whatever that means, is P. What's the probability of a failure? Is 1 minus P. And then what's the number of successes? So here we can use several variables for this. Let's just stick with X. Little x, of course, not big X. Big X is referring to the random variable, right? So once I have these four things, I can figure out immediately the probability mass function of a binomial random variable. So if I want to figure out the probability that my random variable X is equal to little x wait, what does it say? Can P be less than or equal to 0 or 1? Yeah, we normally, it doesn't really make much sense if your probability, I would say theoretically, you can say, right, that the probability is 0 or 1 for a success, but there's not really much to say after that. So we normally deal with binomial random variables whose success is, the probability of a success is strictly between 0 and 1. It's just, there's more to say. If you say the probability of the success is 0, then you're just, I guess the random variable that you're dealing with is not that interesting to really talk about, because you're saying the probability of this event occurring is 0. So probability of the failure would be 1. And there's not much to say after that. So that's why we usually deal with probabilities for success being somewhere between 0 and 1. And so then what's the probability of this occurring, right? This is, if you pay attention to the example that we just did, the number of success, right? This is the number of my successes, being 0, being 1, being 2, or being 3. You see how this is 0, x is 0. We have, well, I should have written it here. I should really introduce 3 choose 0 here. 3 ways, out of the 3 flips, I have 0 heads. Out of the 3 flips, I have 1 head. Out of the 3 flips, I have 2 heads. Out of the 3 flips, I have 3 heads. Out of the n flips, out of the n trials, I want x of them to be a success. That's what I'm saying here. I want my random variable to have x number of successes. What's the probability I have my random variable has an x number of successes? We'll have to consider the fact that there's, out of n of those trials, x of them are successes. If x of them are successes, that means that the probability of that success is p, and there's x of them. So it's p to the x. Same thing we have here. Do you guys see that? Well, in this one here, it's kind of hidden. But here I have 1 head, so 0. My p value here is 0.7, and my exponent is a 1. My p value here, again, is 0.7, but I have 2 heads. I have 2 successes, so 0.7 is being raised to the 2nd power. And then 0.7 here, I have 3 heads, is being raised to the 3rd power. Do you guys see that, the connection? So if I have x number of successes, then I'm raising the probability associated with that success, I'm raising that to the x power. And associated with that probability is the probability of me getting the number of failures. So if I have x number of successes and I'm applying this event or this experiment, I'm applying this trial n times. So out of the n trials, x of them are successes, then that means that n minus x of them must be the number of failures. Do you guys see that? So this is number of successes. And this here is the number of failures. And in a way, I just, in a one single line, I've defined the probability mass function of a binomial random variable. So every binomial random variable has this form for the probability mass function. So the moment I recognize, hey, this is a binomial random variable, I know immediately how to compute the probabilities of a random variable attaining a particular number of successes. It's always going to be, always will be in this form. Okay, so let's see if, yeah, let's see if I can do a quick example, okay? Any questions about this though? So on a multiple, also very common example. That doesn't make sense. Alexandra, no? Oh, no questions. Oh, okay. I thought you meant no, it doesn't make sense. I was like, oh, okay. So on a multiple choice exam with three possible answers for each of the 5 questions, what is the probability that a student would get 4 correct? 4 correct. Let me write this as 4, would get exactly 4 correct. Four correct answers. Do you see how this is a random variable, a binomial random variable? I have 5 separate questions. Me selecting an answer for each question is independent. I can either get it correct or I could get it incorrect. Those are my binary outcomes, right? And I have a probability of getting a correct answer because I'm assuming that one of them is correct and the other 2 are incorrect. So then here, let's break this down. So my binomial random variable x is the number of correct answers. I can either have 0 correct answers or 1 correct answers, but in this case, I particularly want, what do I want? What's my goal? My goal here is to find a probability that my random variable equals 4. How do I do that? Well, I know the formula for it, so I can just break that down. To break that down, I just need to know the parameters. I know n is what? N is the number of independent trials, which represents the number of 5, the number of questions I have, which is 5. What's the probability that I get a correct answer? Well, if I have 3 possible answers, I'm assuming one of them is correct. So then I must have a third, right? So then what is the failure? Would be 2/3, correct? And then what is x? X here would be, in this particular question, would be 4. So I want to compute this. So now I have the formula for it. This would be 5 choose 4 multiplied by a third raised to the 4th power multiplied by 2/3 raised to the 1st power. That's automatically, boom, I'm done. Put this in my calculator. And I showed you how to compute that now using your calculator. You can also do this, by plugging in the same way we just have it, but it would take a bit longer. This is a bit more streamlined. So you have 1 divided by 3. Is this a binomial theorem? Huh. So yeah, we're going to talk about that. Well, the reason why it's called binomial, so I get 0.0411 dot 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 dot. So this is approximately what? 4.1% of the time. So it's very unlikely, right? That you would get 4 correct just by guessing. So the binomial theorem is associated with, there's a connection between the binomial theorem and the binomial random variable. One way to show that connection is if you were to sum the probabilities. For example, that x is equal to x, right? If this is a random variable, and if you were to sum these up, n choose x, p x, 1 minus p, n minus x, and x goes from 0 to n, this is associated with the binomial theorem. The binomial theorem, right, is for those of you who've seen it, and I'll end with this. The binomial theorem is n choose I of a to the ith power, b to the n minus I goes from 0 to n. That's when you take a plus b and raise it to the nth power, right? You get a summation of all these different terms. If you notice here, with this here, it's very much similar. The only difference is the x are the i's, and the p here is the a and the b. So if this is my a and this is my b, and I add them together, what does p plus 1 minus p add up to? P plus 1 minus p is 1. And doesn't that make sense? Why does this make sense? Aren't the probabilities supposed to add up to 1? So this is consistent with that notion. But the difference is we're dealing with probabilities. Like we have a more of a, I guess there's a deeper meaning behind the binomial random variables because we're dealing with the probabilities of a certain event occurring. Whereas the binomial theorem, it's the way usually it's taught, the way it's used is just an expansion of a product of 2 terms. But now we're, in a sense, we're like associating all of these different values here, the a's and the b's, with probabilities. So the question is, yes, this is connected. Okay, guys. Is this clear? Is this better understood? The binomial theorem, the binomial random variable.